Hi guys, Kenna here. So today we're going to be talking about phase changes. Now, I know you've already talked a little bit about this in terms of your freshman physical science class, and this is the transition going from solid to liquid, liquid to gas. And we'll talk briefly also about the skips that you may not have talked about in freshman physical science when we start looking at condensation and sublimation. We'll also talk a little bit about how this relates to the kinetic molecular theory we introduced you to, and we'll go ahead and talk about how that relates to those other phases of matter that are not as common in terms of plasma and the Bose-Einstein condensate. Although not as much time because again, they're not as prevalent, at least on our planet. But remember that plasma is the most common form of matter in the universe because that's what makes up stars. All right, so let's take a look at our essential questions. Number one, what is a phase change? Specifically, what is happening and is it a physical or a chemical change? Number two, what is occurring during a phase change? Keep in mind with respect to bonds and intermolecular forces. And number three, can you compare and contrast a thermal insulator to a thermal conductor? So if we take a look, going back to what we already discussed about phases of matter, the three primary phases are solid, liquid, and gas. And as you add thermal energy, remember thermal energy is the average internal kinetic energy of the particles, you switch from one phase to the next. And exactly where that occurs depends on the actual material that you are dealing with. Water is the common example we typically use because we happen to have it in all three forms here on Earth. So most of the matter that we're going to deal with is going to be in these three phases. Probably all of it, at least for our examples. But there are those other two forms of more exotic matter, the plasma and Bose-Einstein condensate. Now remember, we haven't actually found any Bose-Einstein condensates in the universe. These are all things that have been created here on Earth. And so the existence of those beyond the human forcing it to occur is maybe not as common, or maybe doesn't even happen at all. I don't know. Okay. So today we're going to explore the actual process of going from one phase to the next. The first one we're going to talk about is the melting point. Now, the melting point is the point at which you're going from a solid to a liquid. Okay. Different substances are going to have different melting points, and this is because of the differences in terms of the intermolecular forces between the particles, and they're going to vary in terms of their strength. So stronger intermolecular forces require more energy to break, and therefore have a higher melting point. Water melts at 0 degrees Celsius, but iron melts at such a high temperature, about 1500 Celsius. The difference is that the forces between iron atoms are stronger than the forces between the water molecules. Now, when we start thinking about this in terms of specific heat, there's another factor here, but we'll save that for when we talk about it in class. When enough energy is added, the intermolecular forces are completely pulled apart and the liquid becomes a gas. This is the boiling point. So boiling takes place as the liquid bubbles the gas particles out of the fluid as it rises to the surface. Now, when heat energy is removed, we're going to go the opposite direction. We have condensing, where the gas becomes the liquid, and we have freezing when the liquid becomes the solid. And these changes reflect the level of thermal energy. Again, remember this is internal average kinetic energy within the substance. Now, there are two other phase changes that do occur. We don't see them as often, but these are called sublimation and deposition. Now, this is because they skip the liquid stage. So in a deposition, the gas changes directly into a solid without passing through a liquid phase, and the opposite is a sublimation. Now, most of you have seen a sublimation. If you ever have played with dry ice before, dry ice sublimes. Okay, it goes straight from a ice solid form into a gaseous form of carbon dioxide, and you see the kind of smoke that comes out. Now, it is possible, depending on where you're at with respect to dew point and the temperature outside, for frost to occur. And we are in winter. I don't know if we'll get too much of this year, but frost that appears out of the air is a deposition. Okay. Now, when I go ahead and usually talk to kids about this, we like to talk about iodine. Iodine in itself does this exact process. You heat it up, the iodine crystals sublime and become a vapor, and it's cool. This is actually where its name kind of comes from in terms of iodine, is that it turns into kind of a purplish gas. And then that purplish gas, if you cool it, deposits. It does a deposition and leaves behind these shiny little, typically going to be diamond-shaped crystals. Okay, so it's pretty cool process. And I'll attach a picture so you guys can go ahead and see what I'm referring to. So here is all of the changing phases together. We have solid, liquid, and gas, and then we can convert from one to the other. If it's going from a solid to a liquid, it's melting. Liquid to a gas, it's vaporizing or boiling. If we go the reverse direction, gas to a liquid, it's condensing. Liquid to a solid, it's freezing. If you go from solid to gas and skip the liquid phase, you're subliming. And if you go from gas to a solid, skipping the liquid phase, you're depositing or doing a deposition. Okay. If you remember back to your biology days, in order to go ahead and break bonds, we need energy. This we call activation energy when we're looking at a chemical reaction. But even if we're not changing the actual molecules, just breaking apart the intermolecular forces rather than intramolecular forces, you still require energy. Okay. So as you add heat, the energy increases in terms of temperature. But when you get to that boiling point, or you get to that um, thawing or melting point, you're going to see something interesting happen in terms of a diagram of the phase changes. So you see a rising of temperature, and then it's going to flatten out at the point of the phase change because that energy that would be making the temperature warmer is actually being used to go ahead and break apart those intermolecular forces. Okay. Once we have finished breaking apart all those intermolecular forces, you begin to see the temperature rise again. So you actually don't see a straight line from 0 degrees all the way up to boiling, but in fact, you actually see it rise and then a plateau at the phase change. It rises and then a plateau at the phase change as it begins to go up and up. Okay. The graph here on the next slide will go ahead and show this. So this is what I was talking about. When you go ahead and take a look at this process, what you see here is that you see these two plateaus or areas where uh, the actual temperature stops changing. So notice that on the x-axis we have time, okay, and on the y-axis we have temperature. So as time goes on and we're applying energy to the system, either through a stove or a Bunsen burner or something like that, you see the temperature increases until the point where we hit the melting point. Then you'll notice that it hits a flat point. This plateau is because that energy is being used to go ahead and convert or break those intermolecular forces. Again, that's inter, not intra. So when I say IMF, I'm referring to intermolecular forces. Okay. And so once you finish breaking those enough so that the solid now moves as a liquid, you see the temperature begins to climb again until it hits a point where you have a phase change. This is the boiling point. And again, that energy is going to go ahead and break down those intermolecular forces. And when that occurs, it keeps going and plateau stays there until we really get to a point where all those forces are broken and now the gas particles up here are moving much more freely. And so in terms of the amount of energy, it should make sense why the different phases have the properties that they do. Solids have a fixed shape and a fixed volume because there is a lot less energy inside those. Okay, they vibrate, but they do not move freely over each other. We break some of those intermolecular forces at the melting point, and then you start seeing them flow over the top of each other. Still not enough for them to go ahead and escape. This is your cell phone. What do you think you're just... And so just remember that there is no temperature change while the substance is changing from a solid to a liquid or from a liquid to a gas, because that energy is being used to break those intermolecular forces. Okay, so adding energy is going to be what we call endothermic. Endo meaning into, thermic meaning heat, adding heat. So when we go ahead and do this, melting, boiling, sublimation, these are all endothermic processes where we add heat. Okay. The opposite is going to be exothermic, oops, where we go ahead and remove heat. This is going to be freezing, condensation, deposition. Okay. So this is the phase change diagram that I would like you guys to go ahead and use when you're kind of thinking about these phase transitions, okay? We could go ahead and add in plasma. I don't see a point in adding in the Bose-Einstein condensate because it's really only done by humans, okay? So just remember, a phase change is when matter changes from one state, solid, liquid, gas, plasma, to another, okay? These changes occur when sufficient energy is supplied to the system or a sufficient amount is lost. Remember, endothermic or exothermic, and also can occur when the pressure on the system is changed. Now, this relates to the laws that we looked at in terms of gas laws, okay? We're not going to focus as much on those gas laws in terms of the phase change diagram, but it works here as well. So we're going to focus on temperature since this unit is on thermodynamics. Now, the temperatures and pressures under which these changes happen differ depending on the chemical and physical properties of the system. From last class, we learned that specific heat is the amount of heat per unit mass required to raise the temperature by 1 degree Celsius. Water has a very high specific heat, which means that it takes more energy to increase the temperature of water compared to other substances. The relatively large amount of energy needed to change the phase of water is one reason why water is so valuable to industries. This is why it's used to cool power plants and in radiator of your car. It's also part of why humans sweat in order to stay cool through evaporation and dogs pant. Okay. This high specific heat also makes water really important for moderating the climate. Oceans and lakes help regulate the temperature ranges that billions of people experience in their towns and cities. Water surrounding or near cities takes longer to heat up and longer to cool down than land masses do. And so cities near the water will tend to have less changes and less extreme temperatures than inland cities. This property of water is one reason why the United States on the coast and the center of the US can differ so much in temperature and patterns. A Midwest state, say Nebraska, for example, will have much colder winters and hotter summers than Oregon, where we live, which is at a higher latitude, but actually is moderated by the Pacific Ocean nearby. Okay, so hopefully you understand how this phase change diagram works. And again, we could go ahead and add in here this transition to go ahead, let's see here, and add in, oops, I want to go back. Okay, let's go back. Well, you get the idea. Okay, so thermal conductors. Now, thermal conductors are materials that carry heat easily. So remember, conduction happens when a solid, liquid, or gas, but this is going to be through touching because they're so close together. Because the particles in a gas are spread apart, fewer collisions occur, making air, for instance, a really poor conductor of heat. This explains why many materials used to keep things warm, fiberglass, insulation, down jackets, contain pockets of air because they don't transfer the energy from one area to another very easily. Thermal conductors, however, are good at conducting heat. And so these are a lot of the same things that we take a look at when we start looking at electrical conduction later on. But in general, good electrical conductors like silver, copper, gold, aluminum also make good thermal conductors. And we typically would do a demonstration here where we had people hold rods of the same size and go ahead and heat them up over a flame and see which one gets hot first. Depending on the material and the density of the material, we're going to see different thermal conduction. All right, so when we start looking at thermal conduction making things easy to transfer heat, We also have things on the other side, which are thermal insulators. These are good at preventing the transfer of heat. Okay, so an insulator is not good at conducting. And again, this typically applies to electricity as well as to heat. So examples of good conductors and insulators include the following: conductors, metals, salts, especially aqueous salt solutions, graphite, water, human body. Good insulators include plastics, styrofoam, paper, rubber, glass, air. And we're actually going to use this knowledge when we get to our electricity to try and create paper circuits. Notice that paper is a good insulator and graphite is a good conductor. That'll come back later on in this term. So the last thing I want you to think about is heat conduction and the vacuum. Now, one of the reasons that space's temperature is as cold as it is because there are relatively few particles in space to collide with each other. It's not a perfect vacuum, but it's a near vacuum. And for this reason, heat transfer in space is really difficult. We have used this understanding to actually make thermoses because it's a really good thermal insulator here on Earth. So a thermos, the actual thermos mug, actually has two layers, the inner layer and the outer layer. And in between them is actually a vacuum so that you don't see the transfer of heat through the thermos, only through the mouthpiece, where that inner layer connects with the outer layer. And so that's really the only spot that you see a loss of heat. Because the air molecules have been removed between the spaces to create that vacuum, heat doesn't conduct. So you get a little bit where the cap is and where the mouthpiece is, but um, it cools or warms up much slower than it would otherwise. All right, guys. Hope this is helpful. Take care of yourself. Stay healthy, stay safe, and we'll talk to you soon. Bye bye.